Okay, we're going to get started on Module 2 this evening. Module 2, we're going to be spending this week too, so 2 full sessions, and we're going to be looking at resultants of concurrent force systems. Okay, resultants of concurrent force systems. So as we look at our module here, the first section is going to be our learning plan. So I'll be looking at this PowerPoint presentation in just a bit, but you'll notice that it kind of outlines the sections in our chapter of our McGraw-Hill ebook. Okay, if you ended up getting the loose leaf version, then I'll be referencing the pages and such. But this is going to be from chapter 2, and then these are the sections that we're going to be focusing on. Okay, throughout the next 2 times that we're together. The sample and concept application problems that we're going to be doing will be the practice problems that you will be handing in for Module 2. Okay, so we'll be working these all together. All right, so I have referenced each one that we're going to be doing plus the pages that they're going to be on. In addition, once we're done with our practice problems, and you'll notice that that'll be an assignment that you hand in. So if we go to the practice problems, same things are listed as they were in the learning plan. Once we have our practice problems in, then you're ready to start the application problems. The application problems are found throughout the chapter. How this book works is they don't just have an end of the chapter section of problems. They have like a couple sections they go over, then they've got problems right there that pertain to the information that was just gone over. Then they kind of move on to a little bit more in the very same chapter, and then a couple more problems. So I did add the page numbers here for the problems that we're going to be referencing. So for instance, problem 2.1 is on page 26. And then what I have for you is the final answer. This way, as you move along, and even if you're working independently, you'll know if you know, with confidence that you can kind of move on and that you got the problem right. If you can't get the final answer, then that's where questions for me or asking me to work something in class or spending time during our lab is exactly what I want you to do. Okay. But I know people work probably majority of the time, especially on homework, independently. And it's kind of nice to know, did I do okay or not? Am I ready to move on? Rather than just kind of hoping for the best. So all of the problems that I assign for you guys from Module 2 going forward, you'll always have the final answer. You still have to work the whole problem and show me, you know, how you do it, but at least then you know if you're on the right track. Okay. So we'll kind of go back to this, but this will be your, if you would, homework or application problems for Module 2. So I'll go back a level here. And then you'll notice that we have our session recordings. I am recording each time that we get together. So the session recordings for 2026 will be listed here. If you wanted to look at previous recordings, they're going to be here from last year and the year before as well. They're just links to YouTube. So what I'm going to do is I am going to go back to our learning plan here, and I'm going to click on the PowerPoint presentation, the PDF there, and this is going to be what we follow for chapter 2. So if we go down, so the introduction here to chapter 2, it says the objective of this particular chapter is basically to be looking at calculating the resultant forces for any forces that are acting on a body, and then also looking at equilibrium. Now, we aren't going to be looking at equilibrium in Module 2. That's actually going to be Module 3. We're going to continue on in this very same chapter, but the chapter, you know, covers those things. We're going to be focusing on the first thing, resultant forces, to start off with. So in this particular book, and actually McGraw-Hill in general, because we also use their product, if you would, for dynamics, and they refer to things as particles, not in the sense of there's a force on a particle that is really tiny. It sounds like it's a really tiny little bit. It's just, instead of saying a body or a beam or a table, they just generically say the force is acting on a particle. So that's kind of the verbiage that they end up using. So just so that you know, it doesn't mean that it's a tiny little bit. It just means that it's referencing an object, if you would. They just kind of use that verbiage. So let's first talk about resultant. Now, a resultant, and I'm sure you've probably come across this in maybe previous physics classes or maybe even some of your math classes, where you needed to determine what was the result or the end effect, if you would, of the application of at least two or more forces on a particle, a point, or a body. Okay. And a resultant just means that it's the one force that is going to replace as many forces that are acting on that object and have the same net effect on the body. Okay. So, for instance, when we have a vector, a force acting, a vector is always going to be used to represent a force. And in that case, when we have a force has both magnitude and direction. So we have to have a vector. A vector is going to be a line with an arrowhead on it. So the line represents the line of action and how long is going to be its magnitude. So in this case, we could draw to scale 10 units, okay? And in this case, it's pounds, okay? The application of the force. And you'll notice that it's being applied to point A, and it's moving up and to the right because it has an arrowhead on it, all right? So when I'm representing a force, I have to use a line with an arrowhead. That is something I'm going to be looking at. As you guys handed in Module 1 work for me, and at the very end, we were looking at quantities of the components of forces. And something that I noticed a couple of people, and it's so easy to forget, but it's going to be something I'm going to be really looking at, is when you showed the components, sometimes the arrowhead was forgotten, okay? And the label was there, the line was there, but the arrowhead wasn't. So if I have, for instance, a horizontal or a vertical line, and I need to know which direction it's going in, unfortunately, if I just have a line without an arrowhead, I don't know if it's going up, down, left, or right, or in this case, up and to the right or down and to the left. So it is really important to make sure that all forces are represented with a vector. Now, when I have two forces acting independently on a point, an object, a body, okay, and I want to know what is the one force that I could replace those, in this case, two forces with and have the same effect, that is called a resultant. Okay, so down here, I'm going to zoom in just a little bit. I've got two forces. The two red forces here are Q and P. Q is going up and to the right, and so is P, but at different angles, if you would, to horizontal and vertical. And if I want to know what's the one force that would replace those two, I would call that force the resultant. And that's what we see in blue here. That's what we see in blue. Now, as we look at these two forces, as we stated earlier, when we draw our forces out, we can represent them at a scale in the direction that they're being applied. And I can actually graphically or draw this out to figure out what is the resultant. Okay, as long as I draw everything to scale and I draw it so that everything is at the right angle. Now, if I use a tool like AutoCAD or any CAD software, now I can draw them to the exact lengths rather than just sketching them out. And I can get numbers and values that are going to, be exactly what it would be if I would actually calculate those. In this class, we're not going to have time to do the graphical solutions, but they're going to be showing you, and we're going to sketch some of these at the beginning. And they're also going to be the basis of how we calculate things using our trig functions, if you would. Okay, but this is called the parallelogram because, as you can see, the construction here creates on the very perimeter on the outside here a parallelogram. So they're showing the two forces P and Q applying. And then through the end point of each one of those forces, we're drawing a line parallel to the other force. So through the end point, if you would, or what we call the tip of the vector where the arrowhead is, we draw a line parallel to the other vector, which is Q. So you can see that that dotted line on the top is parallel to Q. And then through the end point or the tip of Q, we're drawing a line parallel to the other force, which is P. Where those two intersect up at the upper right-hand corner here of our parallelogram is where the tip or the endpoint of our resultant will be as it starts at what we would call the point of application or the origin, okay? So the tail that doesn't have the arrowhead is going to start there, and it's going to go all the way up to the tip or the arrowhead to that intersection. Drawing this to scale in CAD, for instance, we could physically measure the length of that vector and find out what its magnitude is, okay? But we're going to be, like I said, we'll be sketching this process, but then we'll be calculating using our trig functions to determine what that magnitude is. Now, as I stated earlier, every vector has to have magnitude and direction. So although they're not giving us the numbers here, either by measurement or by some other means giving them to us, our magnitude is going to be expressed in units of force, okay? So maybe this is our P is, let's say, 10 pounds, and our Q is 7 pounds, okay? And we want to find what the resultant is, and the resultant's units then would also be pounds. If we are working in the metric system, units for force are going to be newtons very commonly, and we'll be looking at all sorts that way. But when we are expressing our answers, they not only have to have the number, but we have to include the units as well. So I'll be reminding you of that too as we go along. All right. So we have already kind of talked about vectors. Vectors are going to possess both magnitude and direction. Magnitude is going to be that 10 pounds, 7 pounds, that's going to be its value. And it's going to also, it can also be expressed in the length of the vector. The direction is going to be given two ways: by angle, measured from like a horizontal or a vertical axis, and the arrowhead. That's why we have to have the arrowhead on it. If we don't have an arrowhead on P, we don't know if it's going up and to the right or down and to the left. Same thing for Q and our resultant, okay? Now, the other type of quantities that we can have, so we have vector quantities, which need both magnitude and direction. And then we have scalar quantities. Scalar quantities are going to be quantities that can be fully defined with just one quantity. So, for instance, mass. How many kilograms is something, or how many slugs is something? That's going to be a scalar quantity. We're not interested if it's going up, down, left, or right. It's not a force, okay? Another scalar quantity is going to be temperature, all right? It's just going to be a number, referenced to, 0, okay? Another quantity is time that is scalar, all right? It doesn't have direction, all right? You might say, well, in the future, in the past, but no, it's just 10 minutes or 2 hours or whatever it is, okay? So those are the types of scalar quantities. We aren't going to be dealing much with scalar quantities. We are going to be force analysis vectors. We're going to be working with a lot here in statics. I'm just going to kind of move beyond that. The addition of vectors. The addition of vectors is going to get us what our resultants are. Now, as we start out here, we're going to be adding 2 vectors. So when we add 2 vectors, we can use that and we can sketch out that parallelogram method, or what we call the triangle method. The parallelogram method we've already seen, where we have, in the case of 2 forces, we are going to draw through the endpoint or the tip of each one of those forces a line parallel to the other force. So those are the dotted lines that we see here. The intersection point then is going to be the tip or the endpoint of what would be our resultant, the net effect of those 2 forces. Now, this is where too, sometimes if we just have 2 forces, you can usually get a sense for what the final net effect is going to be. So for instance, when we look at P and Q here, they're both pulling up and to the right. So our resultant should go up and to the right, and indeed it is, okay? If it's going down and to the left, you might have done something wrong. So you always just want to kind of see if you can kind of figure that out. Now, if there's 3, 4, and 5 forces, which we will have, sometimes it's not always obvious which direction it's going to go in. So then you just got to go through the process and make sure that it makes sense. Now, the other graphical method that we can use over on the right-hand side is what we call the triangle method. It is really exactly the same as the parallelogram method, except we're moving forces instead of drawing lines parallel. So for instance, if we start at A here and we leave P in its position, and if we take Q where it was, and we physically move the tail of Q to the tip of P, now what we're doing is you can see we're kind of drawing the vector instead of a parallel line. Do you see that? And now at the end point of that vector is where our resultant's going to go back from the origin up to the end point of the last vector. Okay. The point down here, you're going to notice that we can add these two forces in any order, whether it's P and then Q, or if it's Q first, then P, our resultant will be exactly the same. So we can say that we can add forces in any order and still obtain the same resultant. Okay, so whether you do it in, like it says here, P plus Q, or in Q plus P, same resultant will be gotten. All right. Now, one of the ways that we can get our magnitude is by using the law of sines. So the first sample problem, we're going to be seeing how we can use and find the magnitude of our resultant using the law of sines. So we'll review that in a little bit. And the equation for the resultant is simply adding the two vectors together. So we'll also see an application of this very soon too. The other trig function that we can use is going to be the law of sines. So this is going to be basically a ratio of the length of a side to the sine of the angle that's opposite to it. All right. So once we know where any particular angle is, whatever side is opposite that angle is going to be on the ratio itself. So we'll see the application of this. I am certain that through the math that you've had up until this point, you have come across the cosine law and the sine law. If you're like, oh, it's been a little while, that's okay. We're going to be going over it. We're going to be practicing it. So it'll like come right back to you. Okay. Now the sine and the cosine laws are going to be used to determine the lengths of sides or the magnitudes of vectors and or what the angles are. Okay. And depending on the information we have, we'll kind of point one or the other to be a better option. Okay. Vector addition. Vector addition is when we add vectors or forces one onto the other to find, for instance, a resultant. So we're gonna use our examples to kind of practice that. Vector subtraction is where we change the direction and then we add the vector. We will be using an application of vector subtraction when we're in kinematics, okay, and in basic mechanisms, depending on which one that you have. We aren't going to do it here because in statics, we only use vector addition. So I'm just going to you can kind of see it's there, but we'll get to do it in a different class and apply it there. Resultant of several concurrent forces. Now, we haven't defined what a concurrent force is. So here you're going to notice that a concurrent force system is going to be a set of forces that share the same point. Okay, so if we look down here at this illustration, on the left-hand side here, you're going to notice that I have three forces that all originate, or what we would say have a point of application of point A. Okay, so notice they share that same point. S is going down and to the left, Q is going down and to the right, P is going up and to the right, but they all start at point A. This is called a concurrent force system. Okay, a non-concurrent force system means that they don't all have the same points of application. Now, if I wanted to find the resultant of these three forces, I can't use the parallelogram rule and I can't use a triangle rule because I've got one extra force I've got to deal with. Okay, so to do that, we're simply going to do a method called tip to tail. Okay, and that tip to tail method is exactly that. We're going to start with one of our forces. In this case, we're going to keep P in the same position, and now we're going to move Q. We're going to take its tail. And we're going to put it at the tip or the arrowhead of P. So that's where you see this here. Then we're going to move the S and we're going to take its tail and we're going to put it at the tip of Q. And now basically what we have is we have P plus Q plus S, and its resultant has to have the same net effect on the body as all three. So its tail is going to start at that origin and it's going to point to the last tip of the last vector. Okay, so if there was 4 forces, we would add the next one, tip to tail, and then our resultant would go to the tip of that last vector. Okay, so so again, we can do graphical methods with more than one. You won't be doing that, but it's good to see how those develop. When we do resultants of concurrent force systems, we're going to be using, when there's 2 of them, that parallelogram rule, okay, to sketch them out, but then we'll be using the sine and the cosine laws. And then when we have more than 2, we'll be using the component method to solve for the resultants and figure those out. So let's look at our first sample problem, okay? Our first sample problem is going to be 2.1, okay? And 2.1 is found on page 23, okay? On page 23. So underneath my camera, I'm gonna zoom out here, zoom in a little bit, focus. We are going to find sample problem 2.1. So it says here, we have 2 forces, P and Q. Okay, we've got Q and P. They act on a bolt, A, right here, determine their resultant. So we want to determine the one force that is going to have the same net effect on that bolt as these 2 separate forces are. Now, step number 1 is we are going to draw a little diagram to, define our problem. So as we move along, we're gonna call these free body diagrams. Okay, officially they're not just yet. They don't introduce that in the book, but that's what they are. We're always going to draw a nice little free body diagram. So this is going to be our first practice problem that you're going to be submitting. Okay, so we want to make sure that we identify that it is, sample problem. And this is 2.1. And if you wanted to reference the page number, this is page 23. Okay. Now, the first thing that we're going to do is we are going to draw the diagram of P and Q. Okay. Now, this can be a sketch, but it has to be a sketch that is readable and something that is going to be large enough that you can add the dimensions to. I'm not kidding when I say take the top third or half of your page to draw these diagrams, because we're going to be adding labels and things like that to it. Okay, so we need to draw P and Q. Whenever we are drawing, we always want to kind of show an X and a Y axis for what we're going to be dealing with. So in our case, we've got point A here. I'm really just drawing a vertical and a horizontal axis, traditional X and Y, and then we're going to be showing the Q and P relative to that, okay? Now this is going to be our origin, but on the problem, it's called point A. All right. Now, I always use a straight edge / protractor. I don't always measure my angles. I'm not going to be, that exact with things, because we're going to be using math to get our answers. If you know that you're not great at sketching, then I would suggest getting out just a straight edge and using it to make drawings proportional. But if you're like, I'm pretty decent, freehand, that's totally fine. All right. I'm totally okay with that. But I do it just because. So we are going to draw our first vector. Now, you'll notice that we have P here. Okay. I'm going to leave P in its original position, and P is at about a 20-degree angle from the horizontal. Okay, so I'm just going to draw P about that long. All right, and I'm going to call it P there. All right, I know that P is equal to 40 newtons. All right. At the very least, you always want to show your variable, P. And if you want to show then P is equal to 40, like over on the side as a given, that's totally fine. All right. Now, Q is going, I should put my 20 degrees right here. Q is going up at an angle here. I'm not going to draw it yet, all right? And it is at 25 degrees from P. But I'm not going to show it coming from A, I'm going to show it in that triangle method, adding it to the endpoint of P. Okay. You could show it as a parallelogram, but I'm going to show it as a triangle. Okay. And you'll kind of see why in a little bit. So I know, and I'm doing this for construction, so you can just kind of see how I'm doing it. I'm just doing it very lightly. I'm putting a horizontal line here. And at the end point of Q, or I'm sorry, of P, I'm going to draw the vector Q. Now, I think I've exaggerated this a little bit. I think it should be more shallow, but that's okay. Again, not protracting it. But this angle right here is oh, it is not 25. This one's 45 degrees. Okay, that one's 45 degrees. Now, how did I get that to be 45 degrees? 20 plus the 25. Yeah, so 20 comes from the horizontal to P, and then another 45 up to Q. So from horizontal, Q is 45 degrees. Does that make sense to everybody? Okay. Now, what I've done is I have added these two vectors together. I've got P from my origin, and on the tip of P, where the arrowhead is, I'm starting the tail of Q. Okay, and then it is going out. All right, so my equation for my resultant, because I'm gonna get my resultant here in a little bit. My resultant is going to be equal to P plus Q. Okay, that's the equation. Now, something we have to add here. We are not algebraically adding these together because Q is 60 newtons and P is 40 newtons, and the resultant will not be 100 newtons, will it? No. We are adding vector quantities, so they have magnitude and direction. If these were in line with each other on a horizontal line, it was 40 plus 60, I could say the resultant was 100, okay? But they're not. They're at different angles. So because of that, I have to vectorially add them together, which means I need to use the vector symbol above each one of my variables, so I know that this is not an algebraic addition. Does that make sense to everybody? Okay. Now, I have P represented, I have Q represented. P plus Q, okay? My resultant is going to start back at the origin, okay? Its tail is going to start at the origin, and its tip is going to go to the tip of the last vector, which is Q. So out here is going to be my resultant. Okay. Notice that my tip is going to the tip of Q, the last vector. Right. Okay. Questions? This is review for everybody. Everybody's at least seen this and like, oh yeah, I kind of remember that. Okay. Good. All right. Now, this is kind of set up for us. So what they want us to find, okay, they just want us to find the resultant. So we want to find R, okay? And R needs both magnitude and direction, okay? Because it's a vector, all right? It needs both magnitude and direction. So as I look here, we have a triangle, don't we? And we have equations that we can use to solve triangle problems, all right? The two that are going to come in handy in the very beginning here are going to be the sine and the cosine laws, okay? The sine and the cosine laws. So let's just generically talk about the cosine law, okay? Okay. In its general form, the cosine law is c squared is equal to a squared plus b squared minus 2ab times the cosine of theta, okay? That sounds familiar, right? In its generic form. C is going to be the longest side, right? You guys remember that? A and B are going to be the other two, right? These are going to be the other two sides. And then theta is going to be the opposite angle to C. Okay. And again, in its generic form, because we probably all know it in our head, the ABC form, right? Kind of like the quadratic form, right? That's got the ABC form too. All right. Now, what we have here, we can use the variables for the sides that we have and put it in the form. So our longest side, or the side that we want to find, is going to be our resultant, right? So we're going to rewrite this as, or just directly down below, is going to be r squared is going to be equal to the two sides. This is going to be p squared plus q squared. If you put q squared plus p squared, that's totally fine too, right? Okay. Minus 2 times p times q times the cosine, and we're going to use the same theta. Okay. Now, where is theta located? It's going to be located opposite our resultant, right? So that means if the resultant is here, theta is there, right? It's this full angle. It's the full angle there. Okay. Now, when we look at this, we want to find what the resultant magnitude is, right? That's what we can use this for. We know the magnitude of P to be 40. We know the magnitude of Q to be 60. So we know this one and this one. But we don't know the magnitude of theta. So we would have two unknowns here, right? But can we find theta based on the information we have? Yeah. Okay. So as we look here, we can calculate based on the angles that we already have what theta would be. Go ahead and see if you can figure out what theta would be. And if you're like, dang it, I wasn't ever good at geometry, I'm gonna wait to see. That's okay. Wasn't always my favorite either, but I started to get better at it. Okay. The final answer is going to be 155. So if you got 155 for theta, you are correct. All right. But let's look at how we would do it. So you'll notice that we have this angle of 20 degrees right here, right? With that horizontal line that I used to construct here, okay? Do you see how 20 degrees is also right here? You see that that's 20 degrees? Yeah. So this is 20 degrees and that's 20 degrees. All right. When we look at this horizontal line right here, this full, if I take this as 0 degrees and I go all the way over, that's 180, right? Okay. But I'm not going to use the 45, right? So it would be 180 minus 45, which would be this, plus 20. Do you see that? Okay. So my theta, I'm going to put where theta is equal to 180 degrees minus 45 degrees plus 20 degrees. And my theta then is going to be 155 degrees. Does everybody see how that kind of comes out with the angles that we have up there? Does that make sense to everybody? Okay. That's where straight edges will help. Okay. And if you make things a little proportional and you spend a little time on it and make the diagrams big enough, those will be easier to see. All right. If you make them tiny and you aren't great at sketching, then all of a sudden they get a little harder to see. So I really suggest trying to get out a little straight edge or a protractor. Okay, so 155. All right, that's what we're going to use here. So let's go ahead and put our numbers in place. So my resultant is going to be equal to, and I'm going to put my square root over the entire thing here, and then I'm going to put my numbers underneath. So this is going to be 40 newtons squared. When we're in statics and any classes that you have with me, we are always going to be putting our units in all phases of the problem. In all phases of the problem. Units do not magically appear at the end. All right. If our units come out as we go through and we cancel or we combine the way we're supposed to, and we end up with the proper units at the end, they are our indication that we set up everything correctly. That's why I insist on it. So make sure that you put the newtons with the 40. Okay. Then we're going to be plus 60 newtons and squared minus 2 times 40 newtons times 60 newtons times the cosine of 155 degrees. And everything goes underneath that radical. Okay. Now, when you punch this all in, you should get something that looks something like, and I'm just going to kind of write out my intermittent step. Go ahead and do that. Now, when we work problems, my expectation is that you're doing this on your calculator, okay? Because this way you know how to enter it in. My calculator is going to be different than yours, is going to be different potentially from your neighbor unless they have the same calculator. So what's really nice about example problems and the practice problems that we do, when you actively do them with me, it's going to be easier when you do your application problems because then you'll know for sure you punched it in correctly. So did everybody get 97.7 newtons here? Okay. Now, in our problem underneath the radical, we had newtons squared because we had a square quantity. Now we're newtons squared. But when we take the square root, we not only take the square root of the number, we also take the square root of the units. And when we take a squared units, we take the square root, we get just the newtons left over in this case. Newtons for a force makes sense, right? Our resultant is a force. It needs to be in force units, which are newtons in our case. Okay. Any questions at all? Oopsie. I see that there's if P and Q are the same angle, it would be a straight line. 25. No. See, in this case, you'll notice, David, when we look at, I know what you're asking. So in this case, only if Q would be on a 20-degree angle from horizontal. Even with this 20 here, Q would still be at a 40-degree angle from horizontal, if this would be 20 and 20. Does that make sense? So only if they would both be at a 20-degree angle, then you could add them together, I think is what you're asking, right?
Oh, no, that was for earlier to figure out what
Oh,
the
I'm sorry.
angle was.
Oh, it was a little, oh, it was a couple minutes ago. Okay.
Yeah.
But did it make sense? The 155 as we talked about it?
Yeah, I just did it
Okay,
differently,
okay.
but it got the
Oh,
same thing,
okay.
so
Oh, okay,
it's
good.
fine.
Good, good, good. Oopsie.
I got a quick question as well.
Yeah.
So this is finding like if I were to screw the bolt, it would take 97.7 newtons to screw that bolt on,
No,
or
no, it's not.
no, it's
This is,
like,
if we look here, that would be the torque. So if we were looking at the top down and we would be
yeah,
looking at the center and rotating,
that'd be the
we would
torque.
be trying to determine, how much torque we would put on that. That's
Okay.
not this. This is, it's already in position and now we're attaching, two strings off of it or two cables off of it going in
Okay.
these two
Oh,
directions.
all right.
And now what is the one force that would replace those two? That's what we're trying to.
Got it. Okay, that
Yep.
makes sense. Thank you.
Yeah. Yeah. You're welcome. You're welcome. Good. I'm glad. Yeah. Yeah. We want to try to make sense of these. Like, when would we practically use this? So good. I'm glad you asked that. Okay. So now this is the magnitude of the resultant, the one force that would replace these two separate ones. The one force that would replace the two separate ones. This is the magnitude. But remember, for a vector, we need both magnitude and direction. Now, part of the direction we have, as long as you have an arrowhead at the top, I know mine is like mooshed together here. And I'm going to make it a little bit bigger. As long as you have an arrowhead, that's part of the direction. It's going up and to the right. But to fully define the direction, I need to know what is the angle, okay, from a known axis. So you would either need to get it from the X or the Y. The X just seems to make sense because others angles came from the X direction. So I'm going to go from the X, and we want to know what is that angle right there. And I'm going to call that angle alpha. Okay. I'm just going to call it something other than theta because we already used theta. All right. So I need to find what is alpha. All right. What is alpha? So if we look here, you're going to notice that, sorry, I'm going to take this one out of here because that was part of my sketch. We have our triangle right here, right? We know that we have a 20-degree angle from horizontal. And if we get this little angle in here, I'm going to call this one beta. Okay, if we get this angle right here, if I add 20 to beta, that will be my alpha. You guys see that? Okay. Now, if I know my angle is 155 theta, and I know the side opposite, now I know the resultant, right, is 97.7. Can I find what beta would be? You guys remember the sine law, right? The sine law is we can set up the ratios of the sine of the angles opposite the length of the side that's opposite them, and we can set those equals. So we know the length of all our sides. We know P is 40. We know Q is 60. We know our resultant is 97. We know one of our angles is 155. So we know this one, right? We know the angle, we could say the sine of theta, 155, over the length of our resultant, right? It's going to be equal to the sine of beta over what's its opposite side? Q, right? Q, right? So let me turn the page here. So using the sine law, find alpha, okay? So we're going to use the relationship because we want to find an angle. We're going to put the sines on the top. So we're going to say sine of 155 over the length of our resultant, 97.7 newtons. So we're going to say sine of 155 over 97.7 newtons. Bless you. It's going to be equal to the sine, not of alpha, but of beta. Beta is in our triangle. So if we look here, we want to know what is that little angle there, and then we'll add 20 to it to get alpha. So the sine of beta divided by Q, which is 60 newtons. Okay. So our only unknown here is beta, right? Newtons are units, all right? Beta is our only unknown. So if I take 60 and I multiply it up, so 60 newtons times sine of 155 over 97.7 newtons. Newtons cancels out on both sides, right? And that's going to be equal to sine of beta. Okay. So you'll get a decimal over here. So let's see what we end up getting. It should be 0.2595. It's going to equal sine beta. Now, I'm putting this in baby steps just to be sure we're all getting the same numbers. You don't have to necessarily write this, but I want to see this. So now sine beta, you should get beta equal to 15 degrees. Okay, that's not a final answer yet, but that's the little one inside our triangle. Okay, everybody get 15 degrees? So if we take 60, 155 sine divided by 97.7, 0.2 595, yep. And then second function sine on mine, and that's 15 degrees. Everybody get that? How did I do what? You have to on your, this is this right here. So I'm not sure how to do it on your calculator. So I have a second function sign. So it would be the inverse sign. Okay. Did that work, Lacey? Yeah. Okay. All right. Yeah. And that's why doing the problems, if it's been a while, especially, and it probably has, depending on when you had your math class or the last time you've been kind of, using these trig functions, whether you're using the inverse or the regular, do the sample problems along with me because then you're going to know, oh, yeah, I have to do the inverse or I have to do the regular. It's not our answer yet, okay? So our 15 degrees was right here. So beta is equal to 15 degrees, right? So to get alpha, alpha is going to be, it's going to be beta plus 20 degrees. So that's going to equal 15 degrees plus 20 degrees. Our alpha is equal to 35 degrees. And that's the direction of our resultant. So that fully defines the resultant now with magnitude of 97.7 newtons. And our direction is 35 degrees. Okay. Now, again, how did I get that? If I go back over here, you have to show on your diagram that alpha, this angle is from 0 degrees X to the resultant. Okay. And because we calculated our beta, that was 15 degrees, then we add the 20 because that's outside of our triangle where P is. Alpha is equal to 20 plus beta or 20 plus 15, and that's 35 degrees. Okay. If you have alpha called out here, I should be able to go to your diagram and see where alpha is located here. If you're referencing the resultant, capital R, which I would expect you are, I better see a calculation down here with a capital R, okay? If you call a capital R down here and something totally different or nothing up here, that's not right, okay? So any questions on sample problem 2.1? Okay. All right. If not, then let's go back to our PowerPoint presentation. This is just the words for the problem, and we did it through going through the example. So 2.1, kind of step by step here. Let's look at our next sample problem, which is going to be problem 2.2. Okay, problem 2.2. So this is going to be on the next page, on page 24 at the bottom. We are going to find this next sample problem. So I'm going to go underneath my camera. On page 24, at the bottom here, sample problem 2.2. We're just going to do part A. You can cross off part B. We're not going to do part B for our practice problem here. But we have two tugboats are pulling a barge. So here's the barge right here. And we've got two tugboats. All right. If the resultant forces exerted on the tugboats is 5,000 pounds directed along the axis of the barge. So the axis of the barge is horizontally, okay, along here. Determine the tension in each one of the ropes going to each one of the barges, okay? And then they're saying that alpha is 45 degrees, okay? So there's 30 degrees here up to A from horizontal, and then alpha is 45. So what we're going to do, we're going to start by drawing a nice sketch, and then we'll calculate what we need to. We'll kind of define the problem from there. Okay. So I'm going to go over here. This is going to be sample problem 2.2, and this is on page 24. Okay. And we're just doing part A only. All right. So we don't have to worry about part B. Now, again, first things first, are we going to draw our diagram? So our barge is going to be along this straight line. Okay. And I'm going to show a vertical axis here. And this is going to be point B. All right. And the barge would be over here. I'm not going to draw the rectangle for the barge. I'm just going to represent the front of it at point B with the intersection that we see here. And then that axis, that horizontal axis, which will be the x-axis, is going to be where that barge is going to be pulled in that direction. Okay. Now we have the one of our tugboats is at a 30-degree angle. Okay, going up. All right. And the other one is at a 45-degree angle. So something like this. Okay. Now, I haven't defined their lengths yet. So, but I am going to define my horizontal force going to the right. Okay. And this is going to be my resultant. All right. And my resultant is equal to 5,000 pounds. So this is the force pulling the barge down the river. Okay. And we're using two tugboats, one going up to A and one going down to B. Okay. Now, where A is going to be. So we're going to draw a line. This is going to be going down to B. I'm going to draw a line parallel through my endpoint of my resultant, parallel to what would be B. And then I'm going to draw a line parallel to what would be A. And this is why I have a pencil. I'm going to extend one and erase the end of another. And now you'll notice that I have created a parallelogram, right? Now this one is going up to A, tugboat A. So I'm going to call this one A. And this one is going down to tugboat C. So I'm going to call that one C. I also know that this angle is 45 degrees. I know that this angle is 30 degrees. Okay. All right. Now, our job, we already know what the resultant is. So we don't have to know what, we are not trying to find the resultant for this one because we know it. We know it's 5,000 pounds going horizontally. What we need to find is, we need to find A and C, right? We need to find A and C. What is the force along each one of those angles that the tugboat has to pull it, okay? In order to get our barge to go down the river in a horizontal manner, okay? So now what we've got is, we've got two triangles, right? We've got one triangle here, we've got one triangle here. But they're really kind of a mirror of themselves, aren't they? Do you see that? Okay. Because this line is parallel to this one. This line is parallel to this one. So can I find this angle right here? Do I know what that is? This angle right here. This one right there. Do I know what that angle is? Remember, this line is parallel to this one. Okay. So if I extend this line up a little bit, this angle is 30 degrees, right? Because that's what this angle is. So opposite angles, is this 30 degrees? Yeah, it is. Okay. If this is 45 and this is 30, what is angle theta right there? What's theta equal to? What is it? 105. How did you get 105? Yes, so if I take 180 degrees minus 45 minus 30, right? My theta will be what's left over, 105 degrees, because the internal angles of a triangle have to add to 180 degrees, right? Is it all coming back? So good. Hope you liked it then. You're gonna love it now. All right, so we know what that angle is. We know all three angles. So now this sets up really nicely. We can use the sine law, okay, to find the lengths of each one of those um, those tensions on the tugboat. So I'm going to do A first, okay? So we're going to use the sine law, okay? Now remember, the sine law, we set up a proportion, the length of a side opposite the sine of its opposite angle, right? So if we look at where A is, all right, and I'm going to use it down here. So A is technically this equivalent line, right? Okay. So A is going to be the side opposite which angle? 45 degrees, right? Okay. So we're going to say A over the sine of 45 degrees. Now, whether you put the sine on top or the length on the top, you just have to be consistent on both sides of the equal sign. I like to put on top whatever the quantity is I'm trying to solve for. All right. That's just so it's less rearranging. That's why I put the A here. The last example we did, we were looking for an angle. So I put the angle on the top. But now when I do my equal sign, I just have to make sure that I put the length for my next ratio on the top of the other side. The length of the ratio I'm going to use is I know the resultant is 5,000 and it is opposite the 105 degrees, right? So we're going to say 5,000 pounds divided by the sine of 40, I'm sorry, side of 104 or 105, sorry, 105 degrees. So my only unknown here is A now. So I'm going to take my sine of 45, I'm going to multiply it up on the top. So A is going to be equal to 5,000 pounds times the sine of 45 degrees divided by the sine of 105. So my A should come out to be 3660 pounds. Okay. Now that's the magnitude of the tension in that cable, okay? If I look here, that means I just found the tension in this cable. I know its direction is 30 degrees, so I didn't have to solve for that. So this vector is fully defined. Okay, it's at 30 degrees going up and to the right. And you should have A going up and to the right at 30 degrees. And now the magnitude of A is 3,660. Okay, so that tugboat has to have that ability to pull at that angle with that much force. Okay. But we've got another tugboat. We have tugboat C, right? So we're going to do that very same thing. Now C this time is opposite the 30-degree angle, right? So C over the sine of 30 degrees is going to be equal to my resultant of 5,000 divided by the sine of 105. Now, could I have used A? Yeah. But whenever possible, it's always a good idea to use as much original information that you can. So in this case, the 5,000 was given, or the 5,000 was given to us in the problem, and A is a calculated value. I'm really confident in A, but yet, again, trying to use as much original information. So then C, solving for that, I'm going to have 5,000 pounds times the sine of 30 degrees this time, divided by the sine of 105. My C should come out to be 2,588 pounds. So this is the magnitude of C. For its direction, you should have it going down and to the right, labeled with 45 degrees, because that finishes giving it its fully defined state. That finishes the direction, okay? Any questions on problem 2.2? All right, these are fun. We're not going to do part B, all right? So we're going to stop there with this example. So again, at the very top here, we started with our, if you would, our free body diagram. Identify the elements that we knew or didn't know. Added some angles. And then we solved for the magnitudes of the two unknown forces. Okay? Using, in this case, the sine law. All right. We are going to take our break because I've been talking for a little bit over an hour. So it's a good time to get up and walk around. And then when we come back, we'll continue on with some more examples.